Don't forget, if you've got anything, if you've got speaker, sometimes it's better to have use headphones if you've got them instead of speakers, so we don't pick up any of the outside interference. Sometimes they feed, they loop and feedback. Anyway, so if nobody has any questions, we're going to do. We're going to start another drawing project. It's not that hard, and we'll talk about it after the lecture. And the lecture is pretty good. It's not, the PowerPoint's not too bad. We're talking about tolerancing, using dimensions, and the formatting. So let's walk through that, and then we'll have some time to go over the drawing project, and we'll finish up probably in an hour. So let's take a look at this guy. Again, yeah, I'm not going to pay much attention to any of this. All of the assignments, start dates and due dates are in the outline. Remember last week we talked about, or I should say on Monday, we talked about IT grade numbers. And the lecture on Monday, we stated that as the numbers go down, the tolerances get smaller. And so as that being the case, as the tolerances get smaller, then the amount of operations that need to be done to the features in order to achieve that tolerance become more numerous and more labor intensive. So if you look at this, let's see, Steve is coming in. Howdy, Steve. Nope, I think he just made it. Or he's out. What happened? Oh, there he is. Okay. Hi, Steve. So we're talking about IT grade numbers. And I think I stated on Monday that the lower the number, the smaller the tolerance, which indicates the more operations that need to be done. So if you look at this chart, it kind of basically typifies and exemplifies what I was talking about. If you're going to use a tolerance that's got an IT grade of 4 or 5, then you're probably going to be doing some pretty labor-intensive operations like lapping and honing. I don't know if anyone's ever done any work like that before. But you can see as the numbers rise, the types of machining operations that are available to achieve those tolerances, and in turn surface finishes, when we start talking about those a little bit. The operations run from honing to grinding to turning with super hard tooling to more normal operations like broaching, reaming, turning, boring, milling, planing and shaping, and so on and so forth. So if you're trying to put a clearance hole in a part for a bolt to go through, you don't want to specify a tolerance on the diameter that's got an IT grade of 4 or 5 or 6 or 7 or 8 even. So where they have to kind of they have to do some major operations to achieve it. You want to use a grade, an IT grade number that's going to allow them to use some basic machining processes. And so this is with respect to the metric tolerancing system. But it really holds true for the ANSI inch tolerance system too. It's just that the numbers that are on the tolerance grades, like RC7 or 3 or RC8, those numbers coincide in sort of with the IT grade numbers, except that the slide that we looked at on Monday that said that as the numbers go down, the tolerance gets looser. I don't believe that's true. I think it's the opposite. If you look at any one of the ANSI tables, it appears to me that as the numbers go up, the tolerances get looser. So that would be the same as the IT grade numbers. And as the numbers go down, it appears that the tolerances get tighter. I'm trying a different set of headphones. I don't know if, can you hear feedback? Did you guys hear feedback at all?
No, sounds good.
I don't hear any feedback at all.
Yeah, it's my hearing aids are feeding back into these headphones. So I don't know, sometimes it's loud enough that people can hear it, and I figure if that's the case, then the mic might pick it up too. So anyway, I don't want to spend any more time on this. When you're selecting a tolerance, whether it's metric or inch, you're probably thinking more about the application, the material, of the parts that are going to be in this this fit system, and things like that. And you're making your choices based on those parameters, not what's the surface finish going to be, and so on and so forth. That it's almost a function of the surface finish is pretty much a function of the tolerance that you're going to wind up choosing. If you choose a tight tolerance with a low number, you're going to have a pretty shiny, smooth surface finish.
Well, it's just basically a chart. If you were unsure what you're going to do, it wouldn't never say anywhere on a drawing or anywhere where there's an IT grade.
Well, it would if you were calling out. Remember the call out for a metric tolerance is like, for example, H11 C11. Or something of that nature. Well, that number 11 is the IT grade. One of the examples we looked at was a.
Oh, okay, I got you.
Right? Yeah. So when you pick the fit, so if you look on the table, let's see, it was A9, I think, wasn't it? Our first one. Yeah, so if you look at the table, we looked at a 30 millimeter loose running fit. There was a H11 C11. So the 11 is the IT grade, and when you look at this, the clearances, we're looking at about 1300ths of a millimeter for the hole, and about 1300ths for the shaft. As the tolerance for that particular call out, and
I got you.
okay.
I just wanted clarification there.
Okay.
We don't have to.
So okay, but I guess because I want to finish it out. So if we're talking an an 11, whether it's H11, it's H11 C11. That means any one of these processes are going to be fine for making that hole in that shaft. We can turn the shaft, we could drill the hole, and we'd probably be okay, because we've got so much clearance, it's not going to matter, if the hole's a little out of round, if the surface finish isn't all that great, it's probably not going to matter that much. So anyway, yeah, let's sally forth. So let's take a look at this. Is a shaft. It's got two diameters on it. Assuming the diameters are okay, excuse me, let's look at the linear dimensions right here. And if you would, See if you can tell me what's wrong with these dimensions. We got basically two issues here.
Just taking a quick glance at it, most of the dimensions on the top of the part there are only going to the hundreds place, but everything else on the sides are going to the thousands place.
Yeah, so you're correct. We have an issue with decimal places. These appear to me to be inch dimensions, and so the rule of thumb is that if the base dimension is 3 places, then the tolerance numbers have to be 3 places also. So that's correct. You know, or I guess the other side of the coin is maybe these numbers should be 2 place dimensions. Okay, but if you're, you know, it works either way. You know, if it really doesn't matter that much how long this dimension is, you know, you've got a pretty loose tolerance here, plus 10 thousandths and minus 20 thousandths. This could probably be a 2 place dimension. Same thing for all the rest of these. Okay, so what's the other issue?
It looks like the tolerances for everything on the top is all over the place.
Can you clarify what you mean by all over the place?
Yeah, there's just looking at it, the 2.0 it has a tolerance of a plus 0.01 or minus 0.02, and then the 1.0 is has a tolerance of plus 0.00 or minus 0.01, but the overall length that says 3.0 has plus 0.00 and minus 0.02. So the tolerance, if anything, it should be consistent all throughout, shouldn't it?
You don't necessarily need to put the same. If we got +1 minus +01 minus 02 on this one, it doesn't necessarily mean this one should be +1 01 and minus 02.
What I was more trying to allude at, sorry, was that at the very least, I think the 3.0 should have like plus 01 in it, because if you're going to have your 2.0 reflect that, I feel like the overall length should also reflect that.
Yeah, okay, so you're fairly close. The fundamental issue here is that these 3 dimensions together over-define this part, because these 2 dimensions here already define the overall length, don't they? If I add this to this, it's 3 inches, right? Plus 0.01, and then minus, could be minus 0.03.
Yeah.
Right? So that doesn't add up to this right here. So the system is over-defined because we have too many dimensions here. We need to get rid of one of the dimensions. Whether it's this one, or this one, it doesn't matter. What matters is the design intent, because if the design intent is to control this dimension and this dimension, then we need to get rid of this. If the design intent is to control these 2, then we need to get rid of this one. And finally, if the design intent is to control these 2, we need to get rid of this one. Because if we take the overall and subtract this, we're going to get this. The only difference is what the tolerance is going to wind up, because we have to kind of add and subtract these tolerances together. That's where the real issue comes in, is that when you look at these 2 together, they could be, if I added these 2 together, my tolerance for the overall could be 3 plus 0.01 minus 0.03, and that doesn't add up to this. Correct?
Yeah.
Okay, because whenever I have these 2 dimensions like this, I have to add the tolerances together when I'm considering the overall. Is that confusing, or is that fairly understandable?
I feel like that makes perfect sense.
Everybody else okay with that? Cassandra, what do you think?
I'm good.
Yeah, I got it.
Okay. Then I'm not gonna dwell on it. So to substantiate what I'm saying, this is what the correct answer slide says. So we've got these two dimensions added together are going to give us anything anywhere from 297 to 301, but this tolerance gives us 298 to 3. So they're inconsistent, and the decimal places don't match, which we already covered that. So that was the issue. Okay, so let's look at this example here. We got a shaft again with, which I assume it's a shaft. It doesn't have to be, but there's no diameter dimensions on anything. But we're concerned with the distance between A and B. So in this particular situation, what's the tolerance of the distance between A and B? What is the distance between A and B, and then what's the tolerance? Anybody? What's the distance between A and B? Give me that. All I got to do is add up the dimensions.
110?
No. 110 is the overall from here to here.
That's 70.
70, right? 30 plus 20 plus 20. Because these dimensions define the distance from here to here, here to here, and here to here. So that's the distance between A and B. What's the tolerance between A and B? What's the tolerance on that dimension of 70?
0.3.
Pardon me?
0.3.
0.3?
Yes.
0.3?
Yes.
Okay. I appreciate that because I can hear the zero.
Sorry.
I couldn't hear the point very well.
Sorry.
So yeah.
I'm getting a little closer.
Yeah. No problem. So yes, it should be, the dimension between A and B should be 70 plus or minus 0.3, right? Because all of these tolerances are plus or minus 1, 1, and 1. So we add them together, just like we add the basic dimensions together. Okay, here's the same shaft dimensioned a different way, right? It's datum dimensioned from here to here, but we're still concerned with the distance between A and B. We know that it's 70, right? Because we already established that in the last example. If we take 110 minus the 40, because 110 goes from here to here, and then subtract the 40, we'll get 70. What's the tolerance accumulation between A and B?
.2. 0.2.
Yeah, plus or minus 0.2. So it's 70 plus or minus 0.2. Everybody see that? Again, even though we're subtracting these dimensions, this from this to get 70, we're still adding the tolerance together because this dimension could vary. It could be 40.1, and this could be 109.9, 109.9. That'd be right. 109.9. I think that's right. So if I take 109.9 and 40 or 39.9 or minus 39.9, I'm going to get 70. But it's going to be, is that right? 39.9 minus, or 109.9. I don't know, I can't do it in my head for some reason. It would be 69.9 yeah, it should be 70, right? Anyway.
Yes, that's 70.
Yeah. Anyway, we're still adding the tolerance together, even though we're subtracting the 40 from the 110. because this can vary plus or minus 1, and this can vary plus or minus 1. So if they vary the opposite directions, high or low, they're going to be, it's either going to be plus 2 or minus 2. Okay, one more, I think. How about now? Now we actually have a dimension between A and B. So what's the total accumulation? What's the tolerance accumulation between A and B?
Just 0.1.
0.1.
Yeah, it's going to be plus or minus 0.1. All right? Which is exactly what the dimension calls out. So if you want to control, two surfaces, the distance between two surfaces, regardless of which two they are, then even though we recommend that you always datum dimension, you still need to hold a tolerance between the surfaces that are important, that the dimension provide that tolerance. You can't rely on these other dimensions, like in this example. You can't rely on this and this to provide you with a 70 plus or minus 1. It could, but there's no guarantee that it would, right? If I subtract 40 from 110, I get 70. But if it's 40.1, then I get 69.9, because I'm subtracting 40.1 from 110. So if 110 happens to be a tenth short, now I've got 69.8, and that puts me out of tolerance, because this is what I'm trying to hold. I can go to 69.9, but I can't go to 69.8. Yes? Okay. Calling out metric tolerances. The top two are okay. If you're dimensioning the diameter of a shaft or a hole, the top two are fine. SolidWorks basically does it for you, but SolidWorks doesn't include the tolerance grade in the call out, at least not by default. If you wanted to, I think you have to specify it on your own. But the fact is, if you're calling out the limits of that diameter, whatever it is, shaft or hole, if you're calling out these limits, you're already specifying what the tolerance grade is. So I don't see the need to do it. So I other than maybe put it in parentheses like they did here, with meaning that it's a reference piece of information. The thing that's important to me are the actual numbers. So this is my preference right here, the top one. This one's acceptable. It's just that it lists the tolerance grade first, and then the actual limits, physical limits of the feature in parentheses, as though they were reference information. And I'm not a big fan of that, because it's not reference information. To me, it's the other way around. The bottom one gives you nothing other than the tolerance grade. So if the person that's reading the print to either check the part or make the part, he has to have the tables on hand. And if he doesn't, well, what's he going to do? He's got to spend time trying to figure it out, or at worst case, he's going to take a guess, and just turn the thing and say, well, it's a 20 millimeter. If I get it, close, it should be good. And then when you look at it here, well, it's, fairly tight. Tenth of a millimeter is 4 thousandths, right? So this is about 4 to 5 thousandths over, I guess, to about 10 thousandths over the nominal. That's fairly loose. He could probably, without even, if he's a good machinist, he could probably get it within that to begin with. Although he could be under. Most likely, he's good enough that he's going to go under this number right here and be a lot closer to the, perfect dimension. So you don't want to make him guess. You don't want to make him guess. Jonathan?
Yeah.
There's some like whooshing sounds coming out of your microphone. I don't know what that is. Yeah, I muted you for a second and then they went away.
I thought I was muted. I didn't realize that. Sorry.
Oh. That's not a problem. So now we're looking at information on how to control the decimal places with metric tolerances. This is a good way to write them. If most metric dimensions are going to be whole numbers, no decimal places, although they will have, but regardless of whether there's any decimal places, if you've got an even number, 1, 40, 35, you don't need to add a decimal point and zeros after that number. And the tolerances don't have to follow a specific pattern with regard to the primary the dimension, the basic dimension. So if our upper or lower limit is 0, we don't have to add any zeros after the decimal point. We don't have to have 0.0. We don't have to have a 0 before the decimal point. But if we have any numbers to the right, then we have to, that are less, and the whole number is less than 1, then we have to show 0 for the ones column, and then whatever our tolerance is, after the decimal point, for however many decimal places it goes. So let's see what this thing says. When you show a single 0, you show it without a plus or minus sign. So we know it doesn't, remember, the 0 integer doesn't have, is neither plus nor minus. And then, let's see what the second one says. If you have plus and minus values that are other than 0, then you should have the same number of decimal places. So you would show this as 0.25 to minus 0.10, not like so. You still need to show the trailing 0 now so that the number of decimal places match up. If this was 0, then they would both be eliminated, and it would just be plus 0.2 to minus 0.1. And the last one, if you're expressing the tolerance in limits, then again, they should have the same number of decimal places. Even though we say, well, if you've got a whole even number, with no, it's not fractional, you don't need to show trailing zeros. But in this case, that's an exception, because in your limit, the upper limit does have 2 decimal places to show the 0.45. So now the 15, even though it's a non-fractional number, still needs to show the trailing zeros. It sounds more complicated than it is. And you know what? If you put 0.0 up here, nobody's going to care. They're going to know what it is. They're still going to know it's 0. So if you don't think about it, and you're writing something out, whether it's a spec or a hand sketch or something like that, as long as your information is clear, If you're not following form exactly, nobody's gonna come after you. So SolidWorks again does pretty much all of this for you, so you don't have to worry about this too much. Like I said, unless you're writing something out like a note on the drawing or a spec that you're putting together for something, then then you'd have to be aware of this, to some degree. The number of decimal places in the basic dimension doesn't have to match the number of decimal places in the tolerance. So in a situation like this, where you've got plus or minus 0.15, you don't have to add, again, the trailing zeros to match the number of decimal places in your tolerance. And I think wasn't that fairly obvious here? Like this right here. I mean, that's fairly obvious there too. You don't have to add any decimal places. Same thing with the top one. Okay, now inch decimal places and inch tolerances. Now everything has to match, right? So in this case, it depends on what drives it, I guess. But if the tolerance is only to 2 places, like it was in our shaft, one of our that first shaft drawing that we looked at, excuse me, then it seems like there's no need for the basic dimension to be 3 decimal places. We could be 2 decimal places and that'd be fine. Because our tolerance is only held to 2 places. But if our tolerance is held to 3 places, then the basic dimension should match. They should always match in the inch system. Whatever the decimal places are, whatever's dominant, whether like I said, the tolerance is dominating or the basic dimension doesn't usually dominate. I'm going to rephrase that and just say the tolerance decides what decimal places you need to show for the basic dimension. Let's just keep it at that. I think that would be safe. So when we look at these 2 examples, this example and this one right here, everything is 2 place. The limit dimensions are 3 place. I mean, excuse me, they're all 3 place. So the basic dimension and the plus minus value should have the same number of decimal places. I've already beaten that one to death. Again, both values of the limit should have the same number of decimal places. And again, I think the tolerance is what drives that. So let's just keep that in mind. How do you control decimal places with inch dimensions, or inch tolerances? I'm sorry. For the last time, the number of decimal places in the basic dimension should match the number of decimal places in the tolerance. You're going to be hearing that in your sleep. We've said it so many times. For angular dimensions and their tolerances, if there is a tolerance on an angular dimension, whatever the decimal place of the tolerance is what decimal place we should show in the angular dimension, the basic angular dimension. So even though it's an even number, and normally if there was no tolerance on this, it would just be 30 degrees. There would not be a 0.0 or 0.0. You don't need to show the leading zeros when it's when it's an even numbered angle, and it doesn't matter if it's 31, 32, 33, 37. But if it's 37.5, then obviously you got to show a 0.5, as long as there's no tolerance. But if there's a tolerance, then you need to make sure these match. So a lot of times you will see on a drawing where an angular dimension is done this way. So it's, in my mind, it's not necessarily wrong, but it's not the best way to do it. Does anybody know why? they're not subscribing to this as being okay.
Maybe because somebody would mistake that for 2 degrees, not 0.2.
Yeah, exactly. I think that's the case. So, you know, and then if you adhere to the rule that says that the base dimension and the tolerance have to match in terms of you know, showing decimal places, well, this follows. But I believe you're right. I would think that it's possible that you could mistake this for plus or minus 2 degrees instead of 0.2 degrees because you can't see it. And if you add a zero, a leading zero, then you've automatically said pretty much, hey, I got to have a trailing zero here. So you might as well just show it, you know, show it like this. But a lot of places don't. A lot of places will show it like this, you know. And I guess.
Ever seen where there was a decimal on a call out like that?
Say that again, Jonathan.
Have you ever seen where there was a decimal number on an angle call out before?
Oh, sure.
Well,
Yeah.
I've never seen it get that critical. Just curious.
Yeah. Yeah, like, you know, if you've got a really precision die and you've got a draft angle on there, that you might, you know, see a call out where the draft angle might be 5.5 degrees. Or, you know, you can call out angles in minutes and degrees, minutes, and seconds. I've seen some high precision stuff in machine tool where we've had angles on cutting tools that are in degrees, minutes, and seconds.
Oh, okay.
So it does. I mean, it's not, you know, it just depends on what you're working with. So
Usually on the end of a chamfer on the end of a part isn't that critical. That's where I see it.
no, a chamfer it would not be that critical. You know, even if you're using it as a lead-in for a press, you know, situation where you're pressing a shaft into a hole and you've got an angle, you know, like a 15-degree chamfer, you know, to kind of provide a lead-in. Yeah, you wouldn't find that it's tolerance like that. But when you're talking about, say, precision, you know, surfaces that maybe have mating parts that need to be, you know, they're angled surfaces, they need to be parallel. Well, if you, you know, if you look at a block tolerance, what's the usually the tolerance on an angle or dimension, and a block tolerance might be plus or minus half a degree. So if you've got, you know, if you got two surfaces that are basically a degree out that you're trying to mate together, you could have some issues with that, you know, if it's precision. So
I got you. Something that's more functional to the part than I got
yeah, than something like a clearance, you know, or a corner break, which is what a chamfer usually is, a corner break. So yeah, well, that's it for that. That's the last slide. The rest of this PowerPoint talks about the P3 project that we're going to be starting today. Before we get to that, one of your other assignments is this tolerance stack-up worksheet, and it's pretty easy. I did have it open, but I guess I don't now. So let me open this tab. This is what it looks like. And it's basically everything that we covered, you know, or examples of practice for what we talked about today. So if you look at question number 1, for example, it says, what's the nominal value of dimension A and how much can it vary? Well, here's dimension A. So we have to decide what dimensions will equal dimension A. And so I basically worked that part of it out for the class this morning. So I'll tell you that it's 14 plus 8, right? Because I go from here to here, and then from here over to this feature right here, and that's what A is. So it's 22 plus or minus something. The something is what you have to figure out. And there's only 3 problems. So if you don't have a way to print it out and fill it out by hand and scan it, I'll make sure that I'll look at the assignment and make sure that you can do the text entry. If you do the text entry for A, for number 1, you're just going to put in, well, okay, the dimension is 22 plus or minus something for number 1. Number 2 is going to be whatever B is and how much it can vary. And the same thing for number 3. What's dimension C and how much can it vary? So I'll give you a hint on C. I would use this dimension, and then whatever you come up with for A, right? If you take this and subtract A, that'll give you C. If you try to do this minus this, and then figure out what the tolerances are, it's going to be harder to do. But if you come up with the variance for A in this problem, you can use it to determine what C is and what the variance of C is going to be. Got it? Yes, no? Are you all gone?
No, I got it.
Okay.
It's pretty
All right.
straightforward.
Yeah. Okay. I never know, what we're dealing with in terms of your experience. So I just want to make sure that it's fairly clear for those that don't, have a whole lot of time working with numbers like this. So excuse me if I sound simplistic. Okay, so no questions on that guy. Let's look now at the instructions for this P311 part. These are the instructions for the P311 part. Let's look at the assignment first off, because the reason for that is because I want to make sure that you understand when you're looking at these assignments, and I have these links in here, I try to make sure these links are all updated. The part file and the drawing file usually never change, but this guy can change sometimes. And if I make a change to it and redo the link properly, you should see this icon at the end of the link. This one doesn't work because Eagle can't preview SolidWorks files. But this one, if I select it, it should preview that that instruction sheet. And I think if you wasn't sure if you could print from this or not. I don't think you can. But you can go full screen if for some reason you don't have anything to view a PDF with, which I don't know why that would be, but the only issue would be you can't print from it. But I just wanted to let you know that that preview is there, and that's why the links are here pretty much, although it tells you what the point value is. It says that it's going to be a file upload. It's going to be a PDF. Should I change that? No, because you can save to a PDF when you do this in SolidWorks. You just save it as a PDF, and then that's what you're going to submit to the assignment. So this is the assignment. And then if we look at this, the instruction sheet, here's the instruction sheet. So it says, create a detailed drawing of this part. Use the 1.7 checklist. This is the 1.7 checklist. It's everything that we've done so far. All of the checklists knitted together. So chapter 1 through chapter 7, all that information on chapter 4 concerning dimensioning is all in here. You know, group the dimensions, dimension between views, don't cross leader lines, blah, 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 avoid long extension lines. Don't use reference dimensions or gauge sizes if you can help it. Sectioning information, advanced views, and tolerances. These are guidelines for creating them, not instructions on how to do them, but guidelines for creating dimensions, proper dimensions, proper tolerancing and sectioning and all that good stuff. These are the instructions for making the drawing. So it says download the part and the drawing template, update the title block, add a revision block, and hopefully it says update the revision to Rev B, but it doesn't say update the revision block. But it says add change balloons next to any changes since Rev A. So what that would tell me if I were doing this project is that I need to not only rev up the revision information in the title block to Rev A or Rev B. I might just say Rev B right away, because that's what I'm going to wind up with. And you're not going to be doing any checking and swapping drawings out because we're not in class. So I might rev up the title block to Rev B right away. But then I would put, my revision block in, and I'd start my first line for Rev A, and I just, I could call it Rev A, or I could say initial draft, and then I would do everything that it says here, and it says consider, here we go. Be sure to dimension all the features, not just the ones described below. So it's going to be a fully detailed part. So make sure you do that. Add the revision block. Consider the need for any supplemental views, such as sections, auxiliaries, and details. And it says, note that there's a counter bore on the back side of the part. And it says consider choosing, consider this when choosing the views, but it also gives you this information right underneath it. So it says that datum A is the bottom of the part, datum B is the left side, and datum C is the front of the part. So when you look at this picture of the part here, this is datum C, right, the front of the part. So if that's the front of the part, well, then that's pretty much telling me that that's what my front view is going to be. Yes?
Yeah, that seems right.
Okay. So if that's the case, then this is going to be my top view. Even though the bottom is datum A, that's going to, this is going to be my top view then, looking down from it this way. And then even though datum B is on the left side of the part, automatically, if I choose this as my front view in SolidWorks, this is going to be my top view looking down, and then this is going to be my right side view of the part, orthographically. So that leaves me with the fact that I can't see this this counter bore that the instructions are talking about. So you're going to have to add some kind of an extra view in order to show that that counter bore, if you're following these directions. On Monday, I'm probably going to pull in the part to the drawing. I'm going to pull in the 3 views based on what this tells me, and then we're going to talk about how we're going to proceed from there. As far as getting our views done, the rest of this information we're also going to talk about, because I haven't talked to you about how to add GD&T to a drawing in SolidWorks. So I'm going to have to demo some of that information as well. It's not that hard. It's actually pretty easy. Everybody has a little bit of trouble with it, trying to get the datum flags to cooperate like they're supposed to, but other than that, it's not that big of a deal. And so then it says incorporate the update the revision to Rev B, incorporate the checker feedback, which we're not going to be able to do. So here's my, and then do all this stuff afterwards. You're going to add the feature control frames for GD&T in Rev B. So here's my suggestion. Since we don't have checkers to look over your drawings, my suggestion is that you do everything you need to do for Rev A, except for printing it out and exchanging. And then when you think you're done and you've got everything on there that should be on there for Rev A, walk away from it for 10, 15 minutes even, and then walk back and start taking a look at it and see what you find that is either shouldn't be there or should be there and it's not. So whatever you find that you need to add or delete from the drawing to make it a better Rev A, that's what I would put in for my changes, because it says to incorporate the checker feedback as needed. So I would say, for Rev B, I'd say added GD&T and added this dimension, subtracted, removed this dimension, change this number, because you're going to have to do some fits too. So or you have to look up some fits. So it says right here, the 0.47 diameter hole should have a tolerance consistent with an FN1 fit, per Appendix A. So you're going to have to look up an FN1 fit in the table. I don't recall what page it's on. You're going to have to look over on the left side to find the range of sizes, because this is an inch drawing. Range of sizes that your 0.47 falls in, over to an FN1 fit, and you're going to look at those numbers, and you're going to hopefully remember that it's thousandths of an inch we're talking about in that table, and you're going to either add plus minus tolerances or limits or whatever you're going to do for that hole. And for these two holes, they should have a tolerance consistent with an LC6 fit. So you're going to have to look those fits up and provide the tolerances and the limits, however you do them, on the drawing. And maybe I'll do one, just to see, just to show you where we're at, show you how to do it. I'll put a couple extra holes in my part, or an extra hole in my part, and I'll tolerance that one so that you get an idea of what to do. So I won't be giving away exactly what you're supposed to do with the other holes. Okay, any questions?
Sounds good. Can't wait.
Cassandra, you're good?
Yes, I'm good.
Okay, all righty. If that's the case, then I think we're done. Let me look at the GD&T preview. The only other thing that I'd like to discuss right quickly is, did I talk about the GD&T fonting? when you're doing those GD&T worksheets, and if you use this website to try to figure out what all those symbols look like, what you're going to see is this. If you don't have the right font running in your browser, you're just going to see alpha characters instead of instead of the symbols. Well, I upgraded. I couldn't find a way to change the font in the older version of Edge, but I didn't realize there was a new version out there. So I downloaded and installed the newer version of Edge, and it runs on Chrome to begin with. So if you're using Chrome, then it's probably going to be similar to change the fonts. If I go into settings and appearance in Edge, fonts shows up down here, and I can customize my fonts. And for whatever reason, I have to change the standard font. And I haven't been able to find one that includes, all of the alpha characters plus the geo tolerancing characters. But because I have SolidWorks installed, I haven't had Solid Edge installed for a while, a trial version. If I go to SolidWorks, see, these are all SolidWorks fonts. Here's a SolidWorks GD&T font. If I select that as my standard font, then it changes everything that's in the standard, that would be a standard font, to GD&T, which if I go back to the symbols now they're all showing up as symbols. You see that? We went from alpha characters to symbols. The problem with it is that you go to another website and that was using Arial as their standard font. And I don't know, I found one yesterday, but I think it was maybe the post office. No, it wasn't. That's one we looked at this morning. I tried to find, see if Rock Valley's website goes wacko. I don't see anything. But anyway, I found a website that was using the same font for links like this. And so the links were all in GD&T symbols. There were no alpha characters. You couldn't tell what was what. So if you change your settings to get a font that will show these symbols long enough for you to incorporate the information into your worksheet, just don't forget to change it back. So when I go back to Arial on this one, everything should be hunky-dory. And when I go back to the symbols now, you see they're back to alpha characters. So, but at least then I could get an idea of what the symbols mean or what they look like. So I could draw, so you can draw them in that sheet because you're supposed to draw them in. That's the only other thing I had. I'm done. Anybody have any questions? Okie doke. If you do, send me some email, and I'll see you guys on Monday. Again, for those of you that weren't here maybe in the beginning, you're not necessarily tied to this particular time for this. I'm only doing this at the regular class times, but if for some reason 10:30 to noon or so, or however long it goes, works better for you, you can show up to that meeting. And I'm going to let them know the same thing, about the afternoon meeting. Maybe maybe I just assumed we'd all be, like I said to most of us here, we'd all be kind of in the groove to meeting at the same time, the 4 to 5:40. So I thought that would be an advantage to getting people to show up. So maybe what I'll do is put out an email saying, hey, I'm just going to, the same links, the links work for both meetings. If I send out an invite to the morning class or an invite to everybody for the morning class and the afternoon class, it's the same link regardless. Actually, you could probably use the old information to log into this meeting as soon as I start it, because I don't think the ID or the password ever changes. So you can use any one of the links to get in. And if 10:30 works better for you, show up then. It's going to be basically, virtually the same information. Okay.
Sounds good.
Okay. I will see you on Monday at some point.
All right. See you
See
then.
you Monday.
Okay. Thanks, guys. I appreciate it.
Take care.
Thanks for showing up.
Bye.